Okay, let's get started with this afternoon's three reports on the two. First would be a tutorial on learning with meshes. So, okay, I can try. Maybe do it like this and speak up, obviously. Yeah, so the first two tutorials will be on learning with meshes. This is a 2.5 hour tutorial, actually split into two parts. I know that you don't. Oh yeah, you see the slides now, so the projector has warmed itself up. And the first part here will be more theoretical. So I'm going to talk in greater detail about meshes and how to define convolutions on them and how to define pooling on them. And the second part will be denoted to coding session, where we will try a particular type of mesh CNN architecture and actually do something cool with this latent space arithmetic, and we're gonna encode and decode meshes and perform various kinds of operations on them. So yeah, so they have a lot of vertices in this polygon in these polygons, but they're also kind of meshes. So let's just briefly talk about the basic math of meshes and how do we basically work with them. So mesh is actually composed of cells. So we define zero cell, which is a vertex, one cell, which is an edge, or actually a segment of a real line embedded in 3D, and two cell is a face. So faces are actually homeomorphic to Euclidean disks, which means they can be mapped by differentiable mapping from Euclidean disk and back and forth. The basic structure of a mesh is actually it's a tuple of three objects. So the first object is the set of all vertices in the mesh. The second object is the set of all edges, and the third is the set of all faces. So an edge is actually just an edge in the graph. It has two vertices on the edge of an edge, so to say. And the mesh itself, for instance, we will be only working here with the triangular meshes. So it's actually composed of triangles, right? So each triangle is actually three vertices plus three edges. They also have to be glued together. So each one cell, which is a vertex of the edge, should lie on the boundary of either of the faces. So each edge should be connected to first to two faces, like this, and also it should be glued at the vertex points here. It's not always the case, because there can be forbidden configurations. For instance, you cannot have dangling edges or isolated vertices. So you cannot have an edge that basically hangs in a 3D space by itself, or a vertex like this. You cannot have intersecting faces. So you cannot have a face penetrating another face or anything like that. You cannot have non-conforming adjacency. That means that you cannot have two faces that are not connected on both edge and the vertex thing, and you cannot have non-manifold edges. So this is an example of the dangling face, an example of intersecting faces. This is a non-conforming adjacency. So as you can see here, these triangles there, they do not align, so this is not a valid mesh. And this is a non-manifold edge. So manifold mesh means that you can only have exactly two faces that share the same edge. So in this example here, 4 faces share the same edge. This makes it a non-manifold mesh, and that's a forbidden mesh in our interpretation. So we're not going to work with such meshes. You can also treat the mesh as a combinatorial structure, and basically the way meshes are stored, they're actually stored as collections of vertices as three-dimensional points in 3D space. So it's basically an array of n times 3. The connectivity information that you can store either as lists of indices or as an adjacency matrix or anything like that. And how cycles of vertices bound faces. So faces are typically formed in traversing the vertices in counterclockwise way. Yeah, so we actually work with 3D space, so we will typically consider these faces as flat, but for non-triangular faces, they can be non-flat. For instance, this this is a quad face, and it is not flat, and it doesn't have to be flat by definition of a face. So sometimes faces, vertices of a face might be not coplanar. But the edges are always straight line segments in all cases. So we will be working, as I told you before, with triangle meshes here. And the triangle mesh is a polygonal mesh with all triangular faces. All faces are flat, because you cannot have a non-flat triangle. And also faces are simplices, in the sense that they are all convex combinations of their vertices. So any point on a face can be expressed as a convex combination, that is this weighted sum of vertex coordinates, such that the weights actually sum to 1. So a few more definitions to bear in mind are stars and rings. So the star is actually depicted on the right here is a kind of vertex that is formed by the set of cells incident at this vertex. So all the mesh triangles, this is a kind of a singularity point in this mesh. And also the rings. So if you select some face and you want to define a ring of that face, you will be looking at the union of the stars of its boundary vertices. So how to define one ring, for example. So you take this face, you look at all the stars around each of the 3 vertices here. So the first star would be this, the second star will be this, and the third star will be this. So the first ring is a union of these 3 stars. It's a very intuitive notion because, and we will be using it actually later in the practical today, to construct spiral convolutions. So it's basically a spiral or a circle around the face being considered. It turns out that because meshes are actually a geometric and irregular data structure, there has been invented quite a lot of editing operations defined on meshes in order to modify it, because the modification of a mesh does not always yield you a valid mesh, unlike with images, because if you just edit 1 pixel of an image, you will still get an image. This is not so with meshes. So for triangle meshes, some specific operations include refinement and simplification. So refinement is getting a finer mesh, that is a mesh that actually typically has more vertices, edges, or faces, and it is more finely represents your surface. You can have also, of course, the simplification operator that will produce you a mesh with less vertices and more coarsely represent your surface. So, as you can imagine, refinement is actually creating more data, that is splitting some data around, and simplification is actually fusing some of the mesh parts together to get a coarser mesh. So this is how it's done. Some of the refinement operators on a triangular mesh is actually inserting more vertices inside the mesh and create new edges between these newly inserted vertex and the existing vertices in order to ensure it is still a valid mesh according to our definitions. Another example would be splitting the edge. So here I have this edge E and I split it in half along one of the directions, and I insert a vertex and two more edges and connect it to the opposite vertices of the triangle. This would of course split this triangle in two. As you can see, both these operations, vertex split and edge split, will get us, well, 3 to 2 times more triangles here. This means that we can adjust these positions of these vertices and length of the edges in such a way as to represent our surface more finely. Also, you can have a vertex split by cutting the mesh along the edges and actually pushing the newly created vertices apart, actually duplicating such edges effectively. And then you fill this quadrangular hole with the two new triangles. So this is a more complex operation, and it actually, but still a basic one, that actually only creates two new triangles for this large mesh here. Of course, as I've said before, you can have an inconsistent mesh because of a triangle flip after you create a vertex. So if you just create a vertex and randomly assign the edges, you will have a non-valid mesh like this. And these flips can be detected because you have to enforce the orientation of faces globally on the mesh. So they can be detected locally. So you consider the neighborhood of a newly inserted vertex, and all the faces in the neighborhood should have the same orientation. So orientation is defined by a normal. This means we flip the normal of some face that does not conform to the majority of orientations here. Simplifications are basically the opposite of these splitting or refinement operators here. So we have edge collapse that will actually collapse, delete an edge from a mesh and collapse the two triangles that were having this edge shared. So we will remove one edge and remove one vertex and only keep the other one, the other leg of that triangle. So this obviously reduces the number of triangles, it simplifies the mesh. It would also possibly destroy the mesh structure, but then we will also be able to fix that in the same way. We can also merge edges, just as the opposite of the same. And we'll try to keep the convex hull by doing that. We can also delete vertices. So here we delete the valence 3 vertex and just are left with the outlying triangle. We can swap edges. This makes sense if you want to preserve sharp features, because imagine that this E dash is actually lying on a corner of a cube. This means you will prefer the blue edge to the red one. This makes sense. Then it makes sense to do an edge swap. And this is a neutral operator in the sense that it doesn't modify the number of polygons in the mesh. So those are the basic operations that we would like to do with meshes. So as you can imagine, because these operations are very different to those that we typically make with sequences or images or multidimensional n-dimensional tensors, this means that we cannot use the same data structures first and use the same machine learning anymore. And this is what Michael Bronstein has been speaking a lot about in his 2 lectures. So let's first talk about a little bit about the data structures that used to represent the meshes. So of course the most straightforward way of storing a mesh is to encode the geometry, connectivity and topology separately, right? People typically face the challenge of trading compactness versus efficiency, because on the one hand data structures should be compact, obviously, to not occupy too much space and so on and forth, and at the same time they should support the time critical operations such as mesh smoothing, refinement, coarsening and so on and forth. One of the most straightforward ways of storing a mesh is basically this so-called polygon soup, because it's called like this because it basically stores each triangle separately and individually. It doesn't encode any global structure. It's just a face set. So you just store a list of faces, and for each face you store the positions of its vertices. For the general mesh, you could also store, of course, the number of vertices, and or you could do it implicitly for triangular meshes. You don't encode any connectivity whatsoever. You just encode a connection of polygons, and you also don't have to. A funny thing is, you don't have to store it all in memory, because you can, do it streaming way, because all the triangles are independent here. Then another way of doing that is an index structure where you want to avoid replication of vertices. So you store a vertices table and you store a triangles table. For each vertex you just store its position, and for each face you reference the position of this vertices in this vertex table. It will save you half of the space, and it encodes connectivity through this vertex table relation. And typically that's what people basically use. It's implemented in obj, off, and ply files, with obj and ply maybe the most commonly used in 3D printing and scanning. Of course, you can also encode, for triangle meshes, you can encode adjacencies, and it's an extended indexed structure with a little bit of topological relations built in. So for each vertex we encode its position and a reference to an incident triangle. So why does it help? It helps to enforce this locally consistent orientation on the entire mesh. Because you have a knowledge of the orientation of the central triangle here, this means you can consistently orient the incident triangles by propagating the orientation here. Yeah, I'll skip that. that. And also there has been this half-edge data structure. So half-edge is, imagine you have this triangular mesh and you want to also store an orientation. So by orienting edges, it is possible to implicitly encode this orientation also. This means we'll have to duplicate each edge, but then after we duplicate it, we orient the first half edge in direction A and the other half edge in the opposite direction. So this would store us the half topological information concerning the edge and also help us orient the triangles consistently. Yeah. There are a little bit of calculations related to how much bytes you would disturb per vertex, but I don't think this is very important for us at this time. So let us talk a little bit about the mesh neural networks. I think you remember some of what Michael Bronstein has been talking about with mesh neural networks, and you have some ideas about how to define convolutions on these regular graphs. So mesh is a regular graph. Can you give me some examples about how do we define convolution on meshes? Right, so we can consider a mesh as a graph. We can consider it as a mesh, which is a specific graph, and we can consider it somehow else. Right? So try to remember, how do we define convolutions with Michael Bronstein? Yeah, exactly. So one way of defining convolutions with meshes would be to compute the mesh Laplacian, compute its eigendecomposition, and as convolution is just a multiplication in the spectral domain, work in the spectral domain. So this will bring us to the spectral CNNs. But before that, I would like to remind you that mesh is a geometric data structure, and in geometry processing domain, we have various formulations of this geometry encoding. So we can, of course, work in the spectral domain like you proposed, but we can also work directly on meshes, and we can we can try to encode the spatial neighborhoods and convolutions directly on the surface of an object. But one tricky thing is that we can work in the parametric domain. That is, imagine this 3D model of the world. So if you just look at the globe, you can cut it along some of the parallels and unwrap it the way this is done for UV mapping and normal mapping and other things in geometry processing when you work with computer graphics for computer games and movies. This will enable us to project the 3D geometry to the two-dimensional map and obtain an image, and on that image we can run conventional convolutional neural networks. This is an area that hasn't been explored, and well, I mean, not sufficiently enough probably, I think we will see a lot of progress in the upcoming conferences. And what we will focus instead on is these spectral domain convolutional neural networks. So the first way of doing it in spectral domain is, of course, compute the mesh Laplacian and decompose it via eigendecomposition. And as Michael Bronstein has reported, if you just look at the eigenfunctions, they have a clear meaning. So the magnitude of the eigenfunction represents meaningful parts of the mesh. The way you would proceed then is, and I'm just repeating Michael here, you would express this convolution in the spectral domain via plane matrix multiplication. So you would do a Fourier transform multiplied with a spectral filter, and there have been a lot of spectral filters developed with this Chebyshev and other networks. And then you would do an inverse Fourier transform and put it into a nonlinearity. This is how you basically obtain a spectral CNN. I will not talk in detail about that, especially given that I don't have enough time. But you can imagine working on in the spectral domain with polynomial filters, with rational filters, and so on and forth. And some of these networks have clear advantages. For instance, it only stores you O of 1 parameters per layer, and so on and forth, and has scale invariance and so on and forth. But I will be working with spatial convolutions, spatial convolutions, and it is really unclear about how do you define a grid-like structure on a mesh. So remember, a mesh depicted here in gray is irregular, so it is not a grid in any way. So one way about how to go about sort of synthesizing this grid-like structure on a mesh is that you select a vertex. This is the I in the large black circle in the middle, and you define a local system of coordinates around I. For instance, a geodesic polar coordinates. You can do whatever you like, spherical, Euclidean, whatever you want. Then you will have to interpolate the signals. So with each vertex there is n-dimensional signal associated. This is a feature vector that lives in that vertex. And we would like to convolve with that feature signal. So we cannot convolve with a feature signal that lives in the vertex directly, but what we do instead is we define this local coordinate system, and we resample the feature vertices living in the vertices, the features living in the vertices, into a grid defined by this local coordinate system. So for instance, I can define, so I'm basically defining these 8 spatial places here depicted in red circles, in red ovals, and I interpolate features across this entire grid into each of the 8 in the 8 ovals here. In this way, I will be able to compose meaningful, fixed dimension, regular spatial representation of this mesh structure in the feature space. So each of the ovals will then have this feature vector associated with that. How do I compute this feature vector? This is done via patch operators. So in this case, you have this local coordinate system uij associated with each vertex, and you have weights that depend on the coordinates in this local coordinate system with respect to the central vertex here. So what you do is, for each of these ovals, you just compute a weighted sum of the feature vectors that live in the entire mesh here. This is this weighted sum. You can think about it as kernel regression or something like that. So this is just feature interpolation. And then you can just have a normal convolution. That is the vector-vector multiply, this inner product of 2 vectors. So of course you can have a lot of various patch operators. Yeah, question? Capital what? capital L is the number of ovals here. Empirically, it's deep learning. Yeah. Which plane? There's no plane. Yeah, so this is a, you can imagine that this is a local tangential linear subspace that is touching this mesh in this vertex. Yeah, so you define a little, a number of locations on this, around the vertex like this, and this is your local neighborhood for the vertex. And then it now has meaningful features, and it now has regularity. So this is one way of going about the spatial convolution here. So you can have other kinds of neighborhoods defined. You can have so as you can see here, if we define this polar coordinate system like this, you can have let me show you. You can have various angular deviation like this, and various how do you call this in English? You know, linear deviation like this. So they can either be exactly separate, or they can somehow overlap, or something like that. You had a question, please. Yes. So it's going to be small n. Yeah. So okay. I would say that n should be the number of spatial locations that you resample to. So it's for here it's 8. That's what I understand, right? So this. So xi is a feature defined in vertex I, xj is a feature in vertex j, and so on and forth. And then what we do is we compute the weighted sum of these features. We basically average across a neighborhood with weights depending on how far they are apart, right? That's what the patch operator does. You see this blue patch operator? Yeah, so that's the averaging with respect to the over the spatial neighborhoods. Yeah, okay. Okay. Yeah, it's a good question. Actually, there has been a number of ways of defining these local coordinate systems. Sorry, what is going on? These are the people always generally work with the polar coordinate system because they are kind of natural. Because you put the vertex in the center, then you create a sphere or a circle around it, and then you will be able to compute these polar coordinates for each of the vertices. But I believe you should construct a plane that is tangential to the surface, and you project to that plane. These are your polar coordinates. Yeah, sometimes, yeah, that's true. Right. Yeah, yeah. I would do for the closest few points, closest in the geodesic sense, right? So you take like ring of rank 3, like maybe the set of vertices with depth of up to 3 from the current vertex, right? Yeah. You can also do maybe this answers your questions better. The geodesic polar coordinates. So you just define them directly on the mesh. Yeah. Okay. And this is just one way of defining the spatial convolution, and another one is like this. So in this case, we were working with features that live in edges, in vertices. But let us work with features that live on edges throughout, like instead. So how do we do that? This is a work by a great team from Israel. They have developed this mesh CNN architecture. So mesh CNN is a mesh convolutional neural network that operates directly on unstructured meshes. So they have defined, and it's a very intuitive thing, they have defined the convolution that convolves across edges in a mesh, and they have defined pooling operations that pulls across edges on the mesh. So let us define that, look at that more closely. So let us define convolution that will work on edge E, depicted in black here. So edge E, because we have a triangular mesh, is incident with two triangles. Even though the mesh is correctly and consistently oriented, we still have two valid orderings in this set of edges. So we either order them using ABCD or CDAB. And we would like to define a convolution operation that will convolve across these two triangles, convolving with features defined on these two triangles. So how do we do that? We first build symmetric features out of the features defined on these four edges, depicted in red and blue. So we basically add and subtract them and do the absolute value of that. We, in this way, we are able to build 5 features and 1 free term. This will give us a 5-dimensional feature vector that characterizes these 2 triangles. Then we just convolve with a learnable filter weights over these 5 features. This is the mesh convolution operation. The mesh pooling will then look at the activations induced by the mesh convolution in the previous layer, select the highest activation that will, the highest activation will of course correspond to one of the edges here, and it will update the topology of the mesh by collapsing edges that have the lowest activation. This means that the mesh pooling operation will actually perform mesh coarsening or mesh simplification according to the values of activations that were computed on the previous step. This is a nice video, and I actually encourage you to read this paper in full, and it's very elegant and interesting. And what it does, it will actually simplify you the mesh. So it selects these 2 triangles here. And then it merges, it basically collapses this edge, this interior edge. Okay. So if you try to learn yeah. So you cannot do the horizontal way because there is no edge. No, I mean the red edge is horizontal way. You're gonna do the other way around. So here you compute activations on each of the 5 edges here, because you have 5 edges. You look at the magnitude of these activations. Some of them are strong, the others are not, and you collapse the edge with the lowest magnitude. And the way you modify features of the resulting edges is by averaging over the triangles that have these edges. So, for instance, in this case, if you have triangle ABE, you would create an edge P averaging A's, B's, and E's features. Okay. So if you work with classification and you would build a convolutional neural network like mesh CNN that performs a series of convolutional and pooling operations, then you will end up with a kind of a mesh simplification procedure that will iteratively coarsen your meshes like this to a lower number of edges, faces, and vertices, and actually compute features on this kind of graph. Here you can see what the iterative coarsening looks like. So it really iteratively lowers the numbers of vertices here. You can do, of course, mesh unpooling, just the other way around. An interesting thing about mesh pooling is it actually spatially adapts to the task. What it means is that it actually leaves you only those parts of the mesh that are crucial to the task at hand. For instance, here is the nice visualization where you have part segmentation results. So the goal is to segment out a part of this volume here, and actually this is what the mesh pooling does. It basically starts removing parts of the mesh, that is edges, that do not correspond to the class being predicted. So the goal is the part segmentation with the meshes. Right, so the next part will be spiral CNN that we will work with in the practical. One thing about the practical is that it will require you to work with a large amount of data, and I just encourage you